Hey everyone. So in this video, we want to talk about dynamic constraints or how to change constraints during the simulation. And we ended up with this example with a stitch constraint and a little bit of wind here under forces. There is 004 in my case. And then I turned on the visualize for the stitch point so that we can see the stitch constraints as well. So there it is. And of course, we gave the whole constraint package that we used here all kinds of settings. But what if I want to change stuff? Well, first of all, let's talk about how to break constraints, because we kind of already seen that with the weld constraint. And just like with that, in the stitch constraint, like with almost all constraint, there are exceptions, but most of them have that. There is this breaking function. So if I just turn this on and run this, you can probably, you can see that it instantly breaks because basically, currently based on the stretch stress, the forces or the stretching is too strong, so the constraint breaks. So let's increase that maybe to 1 and see what happens then. Yeah, and it still breaks, as you can see. So let's see if we can go higher, maybe 10. And of course, this highly depends on your case. And now we found a number where the constraint is strong enough, so to say, so that no stretch will ever break it. So as I said, currently what this is using is the stretching between the points that are connected here. And this is the stretch stress. There are other things like stretch distance, which means, okay, how far away can the points go away from each other? So you can change it to different things, but in my experience, stretch stress is perfectly fine. If you wanted to, just as a side note, you can actually visualize the stretch stress under visualize, where we also turn on the stitch points. Down here under false color mode, you can also show other things like bend stress, and here's the stretch distance and stretch ratio that we talked about. So maybe it can help you when you visualize that to figure out in what areas maybe a certain effect is happening that you want to use for your braking. So the stretch distance looks like this, very similar. And this is the thing in my experience, stretch distance, stretch ratio, and stretch stress are so similar that I usually don't change them. But who knows, there might be cases where there is a difference between them. In my experience, this visualization isn't super helpful. To be honest, most of the time you don't use any kind of visualization, you just try out different numbers, because even if you see a visualization, you only know where stuff happens, but you still don't know what number you need here in the braking. So this is really just trial and error, really, and it depends highly on your case. So let's say we wanted it to brake, slowly or something. Maybe we can try a threshold of 5. And here you can see, no, 5 is still high enough to keep everything together. Maybe we try 2. And as you can see, it's really just playing around. And here you can see the problem is when I find a number that is, not enough for all of them, but too little for some of them, what I will end up with is, in this case, that some will break and others will stay intact. So very often that might not be what I want, because, okay, now this is not too bad, but as you can see, it took a while before it actually finally disconnected. There you go. Which is nice. If this is something that you want to have, then this is perfectly fine. But sometimes what you might want is that the whole thing, breaks off. Maybe there's some kind of effect where it should react to wind or something. And then this absolute number for all the connections, even though they are different, doesn't really work anymore. So how can we art direct the timing of this a bit better? For this, we can actually try to animate this number. So let's say we want to go from 6, which is probably high enough to keep them all together, and then something around, I don't know, frame 50, it should suddenly disconnect. So let's try that. So at frame 45 or 45, we with Alt we set a keyframe, and then on maybe frame 52, I don't know, we set the threshold to 0.1, which is definitely too low, and another keyframe. And with Shift, clicking on it, we can even see how this changes, and that looks good. So what should happen now is that between those frames, the cloth should suddenly disconnect. But as we can see, nothing happens. Why is that? Well, everything you do in front of the solver will only be evaluated at the first frame. So you can animate as much as you want. it will not actually change the behavior during the simulation. Again, there are cases where this is not a problem. You don't always have to animate this. Sometimes it's good to have a certain threshold that then by some kind of impact will break the connection. But in a case like this, we want to have a bit more control. So what do you do if you want to change those settings over time? First of all, let's set some number here. And as a side note, here the scale by attribute or value or both will not work, because this is just meant to change the number in different areas, but it will not help you to change it over time. So this is not the solution, unfortunately. But whenever you want to change something during the simulation, as we've seen before, you have to go inside of your simulation node. And with a Vellum solver, you can do this as well with double click. And as we've seen before, we are now in the dive target. In Houdini 19, some things have changed. Before Houdini 19, there was only one force output, and this is where you can put everything in like forces, as we've seen. But we will use this as well for what we do next, even though there is no output called properties or constraints or something like that. There's now, though, another node, and we will see in a later video what this is for. As the name suggests, this is for sourcing, but we can ignore this for now. Use the force, even though we're not changing forces in this case, we change constraints, but this will work as well. And the node we need for this is Vellum constraint properties. And the fact that you can find this here shows you that this is what it's for. This node will allow you, when you put it into the forces output, to change any kind of property of your constraints during the simulation. And what we can do, for example, is what was it called? It was called the breaking threshold. There it is. So break threshold, let's see if we find that. And there it is, break threshold. So you can change all kinds of other things that we talked about, the rest length or even the stiffness and everything. So you can actually change the whole behavior of, let's say, your cloth constraint to get harder over time or whatever you want. But in this case, what we want to change is the break threshold. So let's first see what happens if we set this to 0.1, just to double check if it actually does something. And yes, it actually changes the, we left with 6 before, there we go. And this now overrides it to 0.1. And now what we can do, of course, is we can animate this from 6 to 0.1 between frame, I don't know, 45 and 50 or what it was. Now be careful though. In this case, we're lucky because it would still work. But one thing I want to make absolutely clear, the Vellum constraint property will change the settings of every constraint in your simulation, not just the stitch constraint. Because by default, it doesn't actually define where I change the break threshold. Now I was lucky here because the stitch constraint is the only one in our setup that actually uses a break threshold. So this will work here, but you should definitely be aware that you should set this node to one particular constraint. And you can do this up here via group, which makes sense. But now we have a problem because what we can only find here is bend, cloth, line, and stretch. There's no stitch constraint. So what do those groups actually mean? Well, be aware that we use multiple constraints here. So we have the Vellum hair for our line. And this creates currently, when we look at the primitives, when we go to the constraint type here, on those constraint lines, there is also an attribute called type, and this is called distance and angle. So this is important. Only on this hair constraint, there are already two different constraints. And that is, again, distance and angle. And that is because every constraint allows you to export, so to say, a group for each constraint. And here we can see the Vellum hair actually creates two constraints, the stretch constraint and the bend constraint. And both have an output group called stretch and bend. And this is what we found. Now, this is what we found before in our group overview. Now, the problem is the same is true for the Vellum cloth. It also creates a stretch and a bend constraint. Those are actually two different constraints that come out of it. And they also have the group stretch and bend. So be very careful with your group naming here because the defaults are not very good. So this here, for example, we could rename to hair stretch, for example, and hair bend in the output group. Then in the cloth, we could say, okay, this is the cloth stretch to make sure we're not applying something to the wrong one, and cloth bend as a group for the bend constraint. And when we look at the stitch constraints, it's even worse. It doesn't even have the output group activated. So none of the groups that we saw before were actually the stitch constraint. Now the stitch constraint only has one constraint, the stretch constraint technically, which is a bit confusing, but it's all kind of the same thing. But I would make sure that when I activate the output group for the stitch constraint, that I actually call it stitch, because then I later know what this is actually doing. So stitch, there you go. And now when we go into the Vellum solver and check our groups in the Vellum constraint property again, this makes a lot more sense, because now all of the groups actually represent constraints. Not only that, they're actually more. The line, for example, comes from somewhere else. I think this was created in the beginning, and also cloth. So we not only find here groups from our constraints, but also from the geometry. So my point here is you have to be very careful to basically keep your groups clean. Thankfully, we named the constraint group for the stitch constraint stitch. So now we can be sure that this Vellum constraint property will only change that very constraint setup. So, and now we can actually do what we wanted to do. We go to frame 10:45, set this to 6 maybe. It could be 10 or whatever, it doesn't really matter, as long as it's high enough. And then we go to, let's say, 10:55 and set it to 0.1. Again, doesn't matter as long as it's low enough. And now, at the right time, and about now it should break. There you go. Okay, maybe 0.1 was even a bit too high, because you can see, yes, we lower the constraint, but it's still strong enough to keep them together. So quickly what I would change is, let's go to this keyframe, and maybe even I move it a bit earlier so it doesn't take so long to move down to 0.1. And actually I will change this to 0.001, something like that, so really low. And now the whole breaking will be faster. And any day now, there you go. And now we can really control that it completely breaks at a certain point in time, and we have full control over all the settings of our constraint. Now, a small side note on this, using those groups I think is the best approach, because it's the easiest to understand and straightforward. But you can actually use in this group, as we've seen before, other things than just groups. You can use attributes directly. So for example, when we look at the data that comes out of the constraints again, there's much more than just groups, of course. We have rest length, we have, as we've seen, the type and so on. And the type is something that you could use to find certain constraints as well. So for example, out of the stitch constraint, well, a lot of stuff comes out of this constraint down here, because we bring in all the other constraints up here, so we will find everything here. So let's make sure for now that we only see, by disconnecting this up here, what comes out of the stitch. And what we will find is this weird thing, that the type is actually called PT prim. That is because that happens when we activate this function here, use closest location on primitive, then the name of the constraint internally is changing. Doesn't matter, just check maybe what the name of the constraint type is. So if I connect everything again so that it works, we can also use this attribute here instead of a group and say, okay, if the type of my constraint is equal to PT prim, and again, you just have to check what the name of your constraint is, then it will find the right constraint as well. As you can see here, using the type attribute, for example, whoop, will work as well. So there are other ways of solving this problem, not just with groups. Okay, great. So now we've seen two ways of actually finding our constraints properly via the groups or by using the type attribute directly. Now, side effects actually notice that both solutions are a little bit kind of complicated. So they realized there must be an easier way of doing all this. What I'm talking about is that besides the group setting here, the output group in the constraints, at the very bottom under attributes, there's actually now a constraint tag that is by default already set to $OS, which, as we talked about before, I think stands for operator string. In other words, when we middle click, we can see this just is the name of our node here. So in other words, every single constraint that is created holds automatically, without us having to do anything, an attribute on the constraints that saves what node this constraint came from. So when we quickly look into what comes out of our constraints and look for this attribute, And let's just filter for the attribute star tag, and then we will find the constraint tag, which, as you can see, holds the name of the node the constraint was created in. And just like we just used the type attribute, we can now instead also use this. So if we're looking for the attributes that were created by the Vellum stitch 1, we can just type in constraint tag equals Vellum stitch 1. And now when we look at the result, surprise, it works just like it worked before. So this is, in my opinion, actually the most convenient way of working, because here you don't have to do anything. It's pretty straightforward. You just have to know the name of your node. And this is why side effects added it. Sorry for adding this so late. Now you know 3 different ways of finding your constraint. But again, this is relatively new and I wanted to share it with you. So yeah, so this is how you change any kind of constraint properties, including the stretch stiffness or bend stiffness, but we used it here to change the break threshold of our stitch constraint to animate, the breaking off of our cloth here at a particular point in time. For this, you use the Vellum constraint property node in the dive target and make sure you connect this to the force output, not the source output. We will talk about this later. And just make sure whatever you change here, you only change on the right constraint, otherwise you will change it on all the constraints. And for this you can use the group up here, either by using the output group that you can set in the constraint node, or you can even use attributes that you find on the constraints, like for example type. So I hope this is helpful. Thanks very much and see you later. Cheers.